In our previous lesson, we started a conversation about two-dimensional geometric figures, primarily polygons with 3 or 4 sides. In this lesson, I'd like to talk more about polygons with even more than 4 sides, and I'd like to spend some time talking about circles as well. So let's get started. First of all, just like with the previous lesson, there's a lot of terminology to discuss with these polygons. So let's get some of that terminology or that vocabulary on the table now, and then we'll see where we can go from there. So we've already talked about 3-sided and 4-sided polygons. Let's now talk about 5-sided polygons. Those 5-sided polygons are called pentagons. In fact, if you think about it, there's a very large fancy building called the Pentagon, which is the headquarters of the United States Department of Defense. It's called the Pentagon for obvious reasons, and one of them is it's a 5-sided polygonal figure. For those of you familiar with the Bible, it turns out that the first 5 books of the Old Testament are often known as the Pentateuch. So we see P-E-N-T-A at the beginning of that word, just like we have at the beginning of the word pentagon. Now, we can move on to 6-sided polygons as well. They have a special name, and they're called hexagons. You may have heard people working with nuts and bolts refer to a hex nut. That's because a hex nut has exactly 6 sides. And 7-sided polygons are known as heptagons. Now, I have to admit, I don't do much with heptagons, and I'm guessing most of you don't either. But I wanted to make sure you knew the name, 7-sided polygons. They're called heptagons. Next, we have the 8-sided polygons, and they're known as octagons, which is a bit familiar when you think of something like an octopus, which has 8 tentacles. And you and I see octagons in life all the time. If you think about stop signs, for example, in the United States, they are all octagonal in shape. Also, not so well known are the 9-sided polygons, which are known as nonagons. Again, they're not very common, but I wanted you to see their name at the very least. And for our purposes, I'm going to lastly go to 10-sided polygons. They're called decagons. Now that name should make pretty good sense. There are lots of ways in which deca or deci are used in the English language. Of course, our usual number system is called the decimal number system, and that DECI refers to the fact that the system we work in is a base 10 system. And of course, there are words like decade, which span 10 years, and it has that DECA at the beginning. And the Olympic decathlon event contains 10 sports. And believe it or not, December begins with DEC because it was at one time the 10th month in our calendar. So hopefully you'll be able to remember that 10-sided polygons are called decagons for a reason. Now, we could continue on with these kinds of names and do it for the whole lesson if you wanted, but I think we've seen enough of these vocabulary terms which tell us about how many legs a given polygon has. Now, I know I've thrown a lot of vocabulary words at you in this lesson already, but let me mention one other very important term when it comes to polygons. A polygon is called a regular polygon if it is equiangular and equilateral. In other words, all the angles have the same measure and all the sides have the same length. So, for example, a square is a regular polygon. The stop signs here in the US that I mentioned a few moments ago are regular octagons. And that Pentagon building I mentioned a moment ago is a regular pentagon, and so on. Now, before we go any further with this lesson, let's take a bit of time to just practice recognizing polygons based on the number of sides they contain and whether or not they're regular. So, let's begin with the following example. I want you to name the type of polygon that you see here. Well, first, notice that there are exactly 6 sides in this polygon, and that means that we are definitely working with a hexagon in this example. Also, it appears that all the sides are the same and that all the angles are the same. And so we say that this is a regular hexagon. Now, let me make a quick comment. I realize that we did not prove that this polygon was regular. But we're not going to worry that much about being exact when it comes to whether a polygon is regular or not. We're just going to go with our eyes to see whether we have a regular polygon or not. Now, let's try another example of this type where we name or characterize the polygon in question. Look at this polygon here, and let's see what kind of polygon it is. All right, let's first count the number of sides. Well, in this case, there are 10 sides to this polygon. Do you remember what kind of polygon it is then? It is a decagon. Now, the next question to ask is it a regular decagon or not? Well, of course not. In particular, it has one edge which is clearly much longer than the others. And so this is not a regular decagon. I'm simply going to call it a decagon. Now let's look at one last example of this type. Classify this polygon based on its number of sides and whether it's regular. Okay, let's look at it again. The first thing to do is to count the number of sides. And in this case, I see 5. There are 5 sides there, and that means that this is a pentagon. And it appears that all of the edge lengths are the same and that the angle measures are all the same as well. And so I'm going to characterize that polygon as a regular pentagon. Now, I'd like to turn a corner and focus on a really nice result that is most easily seen with regular polygons. It turns out that we know the sum of all the degrees of all the angles inside any regular polygon. Remember how we talked in our previous lesson about triangles and squares, and we knew that there were 180 degrees for all of the angles of a triangle and 360 degrees for all the angles in a square or a rectangle? Well, it turns out we can come up with the same kind of result for any polygon, no matter how many sides it has. Here's the result. The total sum of all the degrees of all of the angles in any regular polygon is exactly 180 times the number which is 2 less than the number of legs. So, for example, a square has 4 right angles inside it, so we know that the total of the degrees of all of those angles is 4 times 90 over, or 360 degrees. But that's the same as saying 180 times 4 minus 2. Where is the 4 minus 2 coming from? The 4 is the number of sides of the square, and then we always subtract 2 in these kinds of problems. And if I do the arithmetic there, I have 180 times 2, because I have to do the 4 minus 2 first, and 180 times 2 is 360. Now, let's look at something like a pentagon. Well, a pentagon has 5 legs, and 5 minus 2 equals 3. And that means that the sum of all the degrees of all the angles in a regular pentagon is exactly 180 times that 3 that we calculated just a moment ago. And if you find 180 times 3, you will get 540 degrees. And so every regular pentagon you write down has a total sum of 540 degrees for all of the angles that are created in that pentagon. Now, with that in mind, let's try another example of our own. Let's find the total measure of all of the angles in a regular octagon. And I'm going to suggest here that if you'd like, calculate this yourself, pause the lesson at this time, and then come back when you think you have the answer, and we'll check it together. Okay, in the case of an octagon, we have 8 sides. That's what the octagon has, just like an octopus has 8 tentacles. And 8 minus 2 equals 6. So the measure of all of the angles in a regular octagon is going to be 180 times that 6. And now you have to do maybe a little bit of long multiplication to work through that. But 180 times 6 is equal to 1,080 degrees. So the total of all the measures of all the angles in a regular octagon is 1,080 degrees. And that's it. That's all there is to calculating that number. Well, I could go on and on with facts about polygons, but I'm actually going to finish that discussion about polygons at this point. Let's now transition to one of the most important two-dimensional geometric figures that is not a polygon, and that figure is the circle. Now, let me start with a working definition of a circle. A circle is a set of points in the plane which are equidistant, the same distance away from a fixed point that we call the center of the circle. Now, it's important to understand two things just from that definition. First, we usually pick the center of the circle at the beginning of the problem or at the beginning of our time of drawing the circle, and then we figure out where all of the points are which form the circle. Maybe all the points which are exactly 4 inches away from the center. So typically we start with the center and then figure out where the points are going to be around that center. The second very important thing to understand is that the center of the circle is actually not a part of the circle. It's just there to help us see where the circle is, but it's not officially a point on the circle itself. So while the center is extremely important when we're looking at circles, we need to understand that that point in the plane, the center of the circle, really is not on the circle itself. Now, of course, you've seen a lot of circles in your lifetime. A wedding ring is in the shape of a circle. The various U.S. coins, the penny, the nickel, the quarter, etc., are circles if you look at them from above when they're lying flat on a table. If you look at their outside edge, you're looking at a circle. And to be completely rigorous, only the outside edge of the coin makes up the circle. A circle is not filled in the way a coin is. It's only that outside edge, which is the circle. And if you stare at the wheels on a bicycle or on a car, you're seeing circular shapes on the outside. Honestly, I'm not sure we could really imagine living life without circles these days. They're extremely important geometric figures. Now, also, thanks to the definition I've given you, it's easy to draw a circle, or at least a shape that's extremely close to the shape of a circle with just a piece of paper and a pencil and a piece of string. Now you should try this, seriously. It's a great way to construct circles, or at least pretty close approximations to circles. Here's the way to construct these things. First, take your string and tie one end of that string to the pencil that you have in your hands. Now, on that string, you now have an end which is just sort of dangling. Push down that end of that string with your finger in the middle of the piece of the paper. Pull the string tight with the pencil on it and start drawing, keeping the other end of the string pressed to the paper and keeping that string tight the whole way through. As you do that, what you will start to draw around on your piece of paper is going to be very close to a circle. Now, it would be a perfect circle if we weren't working with such crude instruments like my fat fingers, for example, getting in the way as I try to get this thing to draw freely around in a circular fashion. If you'd like to draw better circles than what I just described, you can go out and get something called a compass. Now, not the kind that people use to find what direction they're walking in the woods, the mathematical kind of compass. And if you use a compass, you can usually draw really pretty circles with practically no trouble once you've had a little practice. Now, circles have been studied by lots of people for thousands of years. Even the people who wrote the Rhind Papyrus, which predates even Euclid by over 1,000 years, were very interested in approximating the area of a circle. And of course, Pythagoras and Euclid and Archimedes and many others were interested in understanding the perimeter and the area of a given circle. But before we get into the perimeter and area questions that are related to circles, let's look at some terminology that's related to circles in this kind of thing. There are lots of terms we could discuss, but I'm just going to mention a few. First, the radius of a circle is the distance from the center to any point on the circle. Remember, the distance from the center to any point on a circle is the same no matter which point on the circle you choose. That's the whole idea of a circle. So that distance from the center to the edge of the circle, no matter what direction you go, that distance is called the radius of the circle. Next, the diameter of a circle is twice the radius distance. So the diameter is just 2 times the radius. The diameter can also be thought of as the length of any line segment which connects 2 points on the circle, which also goes through the center. So you can think of the diameter as the length of a line stretching from one side of the circle to another, as long as that line segment goes through the center. And if you think about it, the diameter is the largest straight line distance between any 2 points on a circle. So the diameter is very, very important. Next, I'd like to talk about questions of perimeter and area for circles. We talked about those for triangles and squares, for example. Let's talk about those questions now for a circle. Unfortunately, these issues for circles are not as easy to think about at first compared to things like polygons, like squares or rectangles or triangles, because circles are not constructed by drawing a bunch of little straight line segments and then looking at the polygon that you get. Something more complicated has to be done when you want to study the perimeter and the area of a circle. Also, one more quick term. I know I've given a lot of vocabulary to you already, but one more. The circumference of a circle is the distance around the circle. In other words, it's the perimeter of the circle. But we're going to call it the circumference. It's a very special word when it comes to perimeters of circles. Now, you may have heard of other words that begin with circum, which basically means to go around or to carry around. So, for example, to circumnavigate means to travel around the world, often by a boat or a plane or a hot air balloon. And you've heard of circumstances which surround an event. So remember, for us, the circumference of a circle is simply the perimeter of the circle. We're thinking about the distance we would have to travel to walk around a circle. Now, to some really important facts about the perimeter and area of a circle. We should really talk about these as we've talked about perimeter and area of polygons as well. First, there's a cool fact about the ratio of the perimeter of a circle and its diameter. Here's the fact. No matter what circle you choose, no matter how big or how small, it turns out that the ratio of the perimeter of the circle to its diameter is always the same amount. Remember, we talked about ratios a few lessons ago. When I take this ratio of perimeter to diameter, I always get the same number. It's the special number that we call pi. And that thing is going to happen. That pi value for the ratio is going to be coming up no matter what circle you choose. In fact, many people define the number pi as this ratio of the perimeter of the circle to its distance, to its diameter. It's very, very interesting to see pi arise in that way. In fact, you can even try to calculate or estimate pi yourself. Take a circle, any circle, make sure it's of decent size, not a penny, for example. Use a piece of string to measure the circumference of the circle. You can literally lay the string down very carefully around the edge of the circle. And once you've figured that out, how long that piece of string is, pull it out and measure it against a ruler. Then you can also measure the diameter of that same circle with that ruler. Now, divide the circumference measurement that you first took by the diameter measurement. And what are you going to get? Hopefully, you'll get something very close to something like 3.14, which is very close to pi. Now, I promise I've not forgotten about the perimeter or circumference and the area of circles. There's some really cool formulas that I want to show you in just a moment, but I need to take a quick detour and tell you a little bit about the number pi. First, the number pi is a very complicated number. And what do I mean by that? Well, it's been proven that pi cannot be represented exactly by a rational number, by a fraction which has a whole number numerator and a whole number denominator. And one byproduct of that statement is that when you're writing down pi as a decimal number, you will never be able to stop writing down the digits, and there will not be any pretty pattern at the end of the decimal expansion. Now, what do I mean by that? Well, pi does not exactly equal 3.14 because that decimal number stops. Pi is approximately equal to 3.14, but pi is not exactly equal to 3.14. Also, pi cannot be written exactly as the fraction 22 over 7, although it's close to 22 over 7. But I know that pi cannot equal 22 over 7 because 22 over 7 has a nice, pretty pattern when I write down its decimal number. In fact, 22 over 7 is equal to 3.142857, 142857, 142857, and so on. And that 142857 just keeps going and going and going. But pi has been proven to not have such a pattern. It cannot have it. It's not allowed to have a pretty pattern like that. And so pi actually is an infinite decimal number. It just keeps going on forever without a pretty pattern. In fact, it starts out as 3.141592653589793238446 ... And you can see that this is pretty close to 3.142857, 142857, 142857, at least for the first few digits. But they're not exactly equal. And so pi is not exactly 22 over 7, but it's close. Now, you might be saying to me, hey, wait a minute, someone taught me a long time ago that pi equals 22 over 7. Well, if they did, they were wrong. What is true to say is that pi is close to 22 over 7, but it is not equal to 22 over 7. Now, of course, lots of people have been trying to approximate pi for some time. The Rhind Papyrus seems to indicate that the writers of that document felt that pi equaled 256 over 81, and the decimal expansion of 256 over 81 starts out 3.16049. So it's an okay approximation, but not the best. Some believe that Babylonian mathematicians in the 19th century BC felt that pi was approximately 25 over 8, which is 3.125. Again, not a bad approximation. It was Archimedes in the 3rd century BC who stated that pi had to be between 223 over 71 and 22 over 7, which are the two numbers that start out 3.140845 and so on, and 3.142857. He did this by carefully studying a 96-sided polygon, which is some very close approximation to a circle if you think about it. So Archimedes definitely had pi sandwiched between these two fractions, but he never said that pi equaled either one of them, and he definitely never said that pi equaled 22 over 7. And Ptolemy in the 2nd century AD chose to go beyond what Archimedes did, and he studied a 360-sided polygon to try to make it look very, very close to a circle. Can you imagine doing that? In the process, he determined that pi was approximately 3.1416666, which is a pretty good improvement to what Archimedes had done, but it's still just an approximation to the exact value of pi. Now, I'm not going to say anything more about approximations to pi at this point. It's a very interesting historical study to do, to look at those who have studied these approximations. But all I'm going to tell you today is that many mathematicians now know the exact value of pi up to several million, if not a billion, digits. Of course, after a while, it's just overkill to know pi up to, let's say, a million digits. In fact, for our purposes for the rest of this lesson, we're going to just use the approximations 3.14 or 22 over 7 in our calculations. Just remember, they're only approximations. Now, let's get to the circumference, which is the perimeter, and the area formulas for a circle. They're both very important that we know these. They both have pi in them, and both are, I think, pretty easy to remember. Here's what those two formulas say. If you have a circle with radius r, then the circumference of the circle, which we will call c, is equal to 2 times pi times r. And the area of that same circle, which we'll call A, is going to equal to pi times r to the 2nd power, or pi r squared. And that's it. So let's do a few calculations with these two formulas to make sure we have them down. First, let's find the circumference and the area of a circle with radius 10 centimeters. And I want us to use 3.14 here as our approximation for pi. Well, we just need to use the two formulas that I just mentioned. C for the circumference equals 2 times pi times r, and A for the area equals pi times r squared. What is r in this problem? It's just 10. So we can approximate the circumference and the area directly by using 3.14 for pi. C is going to be approximately 2 times 3.14 times the 10. 10 was the radius, or r. And when you start multiplying that out, 2 times 3.14 is 6.28, and 6.28 times 10 is going to give you 62.8 centimeters. So that's the perimeter, if you will, or the circumference of your circle. What's the area? Well, the area is pi r squared, and that means approximately we have 3.14 for pi times 10 squared, or 3.14 times 10 times 10. And that's the same as 3.14 times 100, because 10 squared is 100, and 3.14 times 100 is equal to 314 square centimeters. And we're done. Now, let's look at another example. Here's a word problem that involves circles. Mary has a circular pool in her backyard, which has a radius of 14 feet. She needs to cover the bottom of the pool with a special fabric that's resistant to tearing or to ripping. You don't want all that water to leak out of the bottom of the pool. Should she calculate the circumference or the area of the pool to figure out how much fabric to buy? And I'm going to suggest here that we use 22 over 7 as our approximation of pi in order to figure out the answer. Now, I'd like you to think about this problem for just a moment. Pause the video, think about it, see if you can get the answer, then let's meet back up and see how you did. Okay, first things first. What does Mary need to calculate? Well, if she calculates the circumference of her pool, of that circular pool, then all she's calculating is the outer perimeter distance. That's not going to help her at all. It should be clear that what Mary needs to calculate is the area of the bottom of her circular pool in order to know how much fabric to buy. So just knowing the circumference is just not going to help her, because that's just going to tell her how long the outer edge of the pool is. So now we can help Mary approximate the area of the bottom of her pool in order to figure out how much fabric she needs to buy to cover the bottom of that pool surface. So the area, remember, has a formula for a circle. It's pi times r squared. What is r in our case here? Well, it was 14. We were told that the radius was 14. So the area of this circular bottom pool, if you will, is going to be approximately 22 over 7 for the pi times 14 squared. 14 was the radius. And that means we have 22 over 7 times 14 times 14. Now, if you work with this multiplication as if you were working with multiplication with fractions, and you rewrite the 14s as 14 over 1, what you're going to find is the following. You can do some cancellation between the 7 in the denominator and the first 14 in the numerator. And when you do, you're going to actually find that 22 over 7 times 14 is the same as 22 times 2 times 14, which equals 44 times 14, which equals 616 square feet. So Mary needs to be sure to buy enough fabric to cover at least 616 square feet at the bottom of this pool. Now, by the way, did you see how we used lots of the skills that we've already learned in this course? Doing some of these cancellation with fractions, multiplying multi-digit whole numbers, they both came into play. This material, this fundamentals of mathematics material, really builds on itself as you work through this course. And I hope that you're gaining confidence as we continue to work through this material on arithmetic and how it relates to these geometric questions. Now, I'd like to move forward then and think about the following example. Let's find the circumference and area of a circle with a diameter of 12 inches. And let's use 3.14 to approximate pi. Now, I'd like you to think about this, but I want you to be careful because I've thrown in a little twist in this problem. So pause the video, think about it, and let's come back together. Now, this example is actually more of an example about reading and carefully reading word problems than it is about mathematics. Did you notice that I did not give you the radius of the circle? I gave you the diameter. So I was trying to see if you would catch that as you worked through this word problem. What do you then do if you want to find the circumference and the area of a circle when you're given the diameter? Should you just throw up your hands and quit? Of course not. If the diameter is 12 inches, what is the radius then? Well, it's 1/2 of that 12. Remember, the diameter is 2 times the radius. And so the radius here is 1/2 of 12, which is just 6. So r equals 6 in this problem. And now that you've done that little bit of extra work, you can find the circumference and the area easily. The circumference is 2 times 3.14 that we're using for pi times the 6, that's the radius. And if you multiply that through, 2 times 3.14 is 6.28. So I now have 6.28 times 6. Multiplying that gives me 37.68 inches. That's the circumference. What about the area? Well, it's going to be pi, which we're using 3.14 here as an approximation, times 6 squared, because the radius is 6. And that's the same as 3.14 times 36, and that's the same as 113.04 square inches. Well, we've come to the end of this lesson, and I just want to say that there's much more we could have talked about in terms of geometry. There are more two-dimensional objects that we could have studied, and we haven't even started talking about three-dimensional objects, pyramids and spheres and so on. After all, there are full one-year courses in high schools devoted just to geometry. I just wanted to try to whet your appetite for this kind of mathematics just a bit. My hope in sharing these facts about geometry with you is that you gain an appreciation for how geometry and arithmetic really interact with one another. Next time, we're going to talk about another area of mathematics known as number theory, and we'll return to our arithmetic skills at that point.